it's the same variable.
And also,
It's not just the same probability of 1 and 0, it's when there's a 1, it's always a 1. So if you look at this, analyze it, it's just like you yeah, that was the one we said in the last class. Think of C. You have to think of the two C's as one thing, not just the same probability.
Yeah.
And he shows other ways to do it too. Other students, you can do, no, not class, but he said he showed other students do the truth table all the way down and figure out where it's true and figure out
That we were teaching. And he's a science student.
I kind of like that.
Alex, I can talk to you about it in a second. If you just,
really just.
yeah, please. Otherwise, I'll keep everybody waiting.
Okay, I said it.
I know.
Doesn't die out.
What happened to him?
Okay. That's really weird. Is he going crazy? Is he like separating his skin into two colors now? Well, I don't seem to be cracked.
Well, he cracked a lot.
Because for the first time I saw this on the phone, write it out. So here, I don't do one. That's a lot of I did see it in this one. A and B are like no percent stress. One input file register. Then did the add, did the test on the status register and everything on station.
I mean, is that a real answer?
I don't think so.
Okay.
After
So I drew it in SketchUp. That's a separate rendering program. Shading. That's the impressive part, how good those programs are.
You understood Joe Biden's.
No, I didn't understand it because I couldn't. I tried it. I understood what you said, kind of.
Good. Very good. That's so great.
Yeah, I suppose I could just compute it or do it with triangular square. Like 24, but just use.
What the, yeah, oh, well, I remember trying to come up with how to spread you find this. And then we've got the first side thing of one is that first side one, two, yeah, I saw that. Okay, so then what happens is you stop all those times are efficient and you get this. So and then when you solve this all out, you get like one coefficient x times the second everything efficiency and x squared times and then we'll solve for the first one, put the first one into you get a right answer. I have the right answer.
I feel like I could just not email you.
What about this?
You have like everything from like blocks, this is like with Minecraft.
Yes, yes. Okay, okay.
Not that really, but.
Are you
All right, so today I'll continue with the topic of nanoscale switches for the first half. I'll discuss a different design objective. So instead of seeking to minimize the number of switches that we have to implement a function, we're going to look at how we compute with defects. And then I'll make an abrupt switch midstream to begin talking about chemical kinetics and the model that we'll use. And so for better or for worse, I guess that's what I decided to do this semester, is to alternate between circuits topics and biology topics, and then algorithmic topics. I'm just going to interweave them. It'll seem like a very abrupt switch, from one topic to another. But you'll see, I hope, as the semester proceeds, a theme begin to emerge. And that theme is probability. So you got the sense with circuit design that we're making use of a very novel view of how circuits compute. They compute in terms of probabilities. And everything pertaining to these nanoscale switches is probabilistic. And that's going to be a theme with molecular computing, or the biological computing. Not only that we use probability. After all, using probability isn't so new. It's hard to think of a branch of engineering that doesn't use probabilistic analysis. But the new aspect is, in essence, structuring the computation so that probability is our friend, or that randomness is our friend, and we seek to compute in terms of probabilities. Okay, so the theme here is going to be, I won't give much of a repetition from last lecture, but the theme here is that we're working with switches, or we're working with an idealized model of those switches, where a switch is a device that is either on or off. And in this case, the switches have 4 terminals. So when the switch is on, the 4 terminals are connected. When the switch is off, the 4 terminals are not connected. They're disconnected. And the name of the game is to arrange such switches into a grid, or into two-dimensional lattice, and then examine computation of a function in the sense that the function evaluates to 1 when there is a closed path between two target points, in this case the top and bottom plates, and the function evaluates to 0 when there's no path between them. So, as I explained a bit last time, the motivation for considering these switches is various types of modern nanoscale technologies. And I gave a little bit of an overview of my take on what these nanoscale technologies are. Examples are carbon nanotubes and nanowires, so very small wires that are built not so much by explicit pattern, but by self-assembly techniques. So they're grown in a chemical sense, not a biological sense. But they can be very small and very dense. But, and there's still a tremendous amount of excitement about nanotubes replacing transistors in future computer systems, or perhaps memories built out of such systems. And a tremendous amount of funding. So the various federal funding agencies, in particular the military ones, DARPA and the Office of Naval Research, they're investing in this. But so are the semiconductor companies. There's a consortium of semiconductor companies that jointly provides funding for universities and for research within universities. And they've been pouring, I'm pulling this number out of a hat, but perhaps half of their budget on research has been targeting new nanoscale technologies like this, a tremendous investment. And almost all the work that's being done is, as it should be, at the level of the technology. So figuring out how to manufacture such systems, how to characterize them, and almost no work is being done on, I wouldn't say the architecture level. The architecture level is how you figure out pieces of a computer system should be put together. But almost no work is being done at the logic level. So figuring out, are we going to design circuits with logic gates as an abstraction in the same way? And people kind of assume that we will. But here's a problem, and a problem that if you go to such funding meetings or if you read the reports, it's kind of really striking. People will talk about how the technology in an individual sense, so if you look at how a transistor might be built from a crossbar. So you have two wires, and the wires touch, and how you could potentially build a controllable junction here. So you could build a junction that you can control by applying a voltage that would create a switch in a sense. So a lot of effort to characterize how this junction would behave, how it could be used as a transistor, what its voltage transfer characteristics are, and then a lot of work done to characterize how bundles of these could be put together or built. But people will admit a couple of things. First of all, they'll boast, people who work in the area, at the incredible densities. Like, I mean, we're talking about each wire being a few nanometers thick. So an order of magnitude smaller than the best current semiconductor circuits. They'll boast about that. But then they'll admit that because they're using self-assembly as the paradigm for building such circuits, a couple of things. One, the yields are extremely low. So is anyone here in the class taking VLSI or has taken VLSI? What's your name? Is it with a S? Chopin. Okay, I'll remember that. So Chopin. What are yields in the semiconductor industry? What are they typically? Talk to us a bit about it. Yields in the semiconductor industry.
How many chips you're producing?
As a fraction of what?
I mean, how many of them are usable actually?
Yeah. So this is perhaps the dirty secret of the business, that in semiconductor manufacturing, it's an expensive process, and it yields something that has high value. But what's typical is when you build semiconductor circuitry, you do so on a silicon wafer. You build really complicated circuits, and a lot of them don't work. So there's a testing process, and then some fraction of what you build works. Now, if you come from a background in industrial engineering, let's say you're over in what department makes light bulbs? I don't know what computer department would do research into light bulbs. But GE, when they make light bulbs, they talk about yields. And there they typically talk about yields in the 99.9%, meaning 1 out of 1,000 light bulbs they make is defective. And that would be a very shameful yield for a company like GE making light bulbs. In the semiconductor industry, we're talking about yields that 30% is a good yield for semiconductors. So 70% of the chips that are made are tossed to begin with. And so it's an industry that, to begin with, is accustomed culturally to very low yields. But the people who are demonstrating nanoscale technology, their yields in some of the experimental prototypes, forget about 30%, forget about 1%. They have about 1 in 1,000 devices that they build that they claim has acceptable performance. This is simply because the process of self-assembly is one that has a lot of randomness built in, meaning if you try to, by self-assembly, I can't properly describe it, but you can use various types of deposition. So you basically float your chemicals in solution, and they'll line up, and when they line up, they can continue to line up. And so people strive to get that working. It could be exciting. It could be a way to build things that are very small. But things often go wrong, so you toss a lot of what you build. And the dirty secret is that for self-assembly, they're talking about extremely low yields. That's one problem. But the other problem that's of interest to people like me who are experts in logic synthesis or logic design is they freely admit that not only do they have to reject most of the devices they build, but the devices that they do build function correctly at some rate like 50% by some measure. So it means even those that they don't reject will have perhaps 50% of the switches being defective. So they create a vast array of wires and switches, incredibly dense, incredibly exciting, but full of defects. And they simply state, oh, but since we have so much redundancy, since we have so many such switches, we'll just figure out at the logic level how to cope with these defects. And it's not so simple, because in the area of digital circuit design, the concept of fault tolerance is one that's been studied for a long time. As I mentioned, you have circuits that misbehave because bits randomly get flipped. It's much harder to compensate for than you might think. So, Chopin, what are some techniques for fault tolerance in circuits?
I don't know, maybe you could test them many times, like test once, like you build a few, then test them many times and see which one is actually working.
Uh-huh.
And then build others by that technique.
But, so has anyone heard of TMR? What does TMR stand for?
Triple modular redundancy.
So that's an acronym. It's not the worst acronym in the world. The triple modular redundancy. So basically what this means is, if we have circuits that are going to fail or could fail, what we should do is introduce redundancy. Do the computation several times. So why 3 times? Who said TMR? Why not just do it twice? Pardon?
You don't know which one's right.
Exactly. You have to vote, and that's what TMR is all about. So you do it 3 times. You do the exact same computation 3 times, or you triple the size of your circuitry. And then over here you have a little voting circuit. The voting circuit takes all 3 copies, and if all 3 agree, great. But if they disagree, then it chooses the best 2 out of 3 as the winning proposition. So that's one basic technique. It's ubiquitous in computer systems. But there's an inherent weakness with this. So it was Seamus and Jesse. So Jesse, what's an inherent weakness with this?
You could, if there's some sort of other system error causing the incorrection, it could potentially produce it multiple times.
But another kind of fundamental weak was with the topology. So who's to say that the voting circuit is correct? The voting circuit can make errors. And a basic problem that actually pervades all of the research in fault tolerance at the logic level is you can build a really big circuit, and you can use all kinds of techniques to try to ensure that if parts of the computation introduce errors, you'll correct for them. But at the end of the day, you've got, for each output of a digital system, right at the output, this is going to be a wire that's either 0 or 1. You're going to have some gate producing it, producing the 0 or the 1. If this gate fails, then no matter what you've done in this vast cone, no matter how clever you've been, the error is catastrophic. And so the error that occurs, there's simply no way at the logic level to ensure correctness if there's a chance that you have errors anywhere in the circuit. So the obvious solution is to try to make the voting circuitry when you're doing TMR incredibly robust. So for the voting circuitry, here you might choose, instead of using very small transistors, to use very large transistors because they're less likely to fail from random effects. And so these are all very plausible solutions. But my point, and I should begin discussing the four-valued switches, is that the people who work with the technology who just assume that, okay, we have lots of errors and randomness, but that doesn't matter because we have so much redundancy we can cope for it, may not be so simple how to cope with it. Okay. But in terms of the defects that we'll consider here for the four-terminal switches, we're going to begin. So the basic premise here is that we won't so much in this case be talking about how you lay out the switches to compute a function, even though we'll lay out the switches in the manner that we described last time, in some way to lay out the switches controlled by variables such that we compute a function from top to bottom. But today we'll be concerned with defects, and we'll be concerned about trying to ensure that an individual switch behaves correctly. Now, instead of using an individual switch as an individual switch, we'll use redundancy. So we'll use multiple switches in the place of a single switch. So what do I mean by that? So assume here that you have a switch replicated 9 times. So you take one switch, and you replace that one switch with 9 switches. And all of those 9 switches are controlled by the same variable. So you have redundancy, 9-fold redundancy. And you want to look at whether the 9 switches buy you any kind of benefit. So here, in the ideal case, if you have no faults, that means that when the switch is closed, or when the meta switch should be closed, the larger switch should be closed compared to the micro switches closed. Well, they should all be closed. They should all be black. But in the case of defects, you may get some white switches, which we'll call the open switches, when they should be closed. If in the case when all the switches should be open, so they all should be white, you have some defects. You may have some switches that are closed when they should be open. So here I am blurring between transient and permanent faults. So what do I mean by transient versus permanent, Chopin, in this case?
Well, you never know which one is going to misfunction at which time.
Yeah.
So, but like, as you can see, the switch, which is like third row and second column,
Yeah.
that one is actually misbehaving in both cases. So that's
Mm.
might be actually a permanent.
Oh, yeah. That's good. I'm not being so clever here. I'm just, when I set up these slides, I don't think I was even looking at that. But what I'm just trying to get at the definition. So here, the permanent fault is actually very plausible. The permanent fault is the switch is simply broken, meaning it's either permanently closed, meaning you apply a voltage, it doesn't matter, it's closed, or it's permanently open, meaning apply voltage or not, it's always open. And those are definitely the more common type of faults seen with nanoscale devices. But transient faults are very common too. That's where you have a switch that's maybe kind of working, but not working perfectly. So you look at it one day when the temperature is warm, and it seems to be working, and then it's a bit colder, and suddenly it's not. So it's transient. And the transient faults are the scary ones from a designer perspective, because you can build a circuit, and it can look and function perfectly, and then you ship it off to your client, who happens to be the builder of a nuclear weapons launch system, and that's when it fails. So the transient faults are the scary ones. But in this case, the techniques that I'll show, in a sense, can cope with both. Or, as you'll see in a moment, because it's going to be a probabilistic argument, it really doesn't matter if the faults are transient or permanent. So, okay, here I'm just saying that the faults may be, the terminology is stuck on or stuck off, or they may be transient. So here, then, is just a reminder of the basic premise that we're going to have for computation, which is we're going to have this grid, or this two-dimensional lattice, where we've laid out the variables. So the variables are laid out. Each variable controls a square. But here, I'll use the terminology, what should I use? I can use large square or small square, or large switch versus small switch. Why don't I use the terminology meta switch? The meta switch is going to be a collection of switches. So as I've tried to draw here, what we have is, for each switch, we're going to replace that switch with a bunch of smaller switches for redundancy in here. But the premise is going to be the same as in last lecture. We're going to seek to implement a function that computes 1 or 0, depending upon whether there's a connection between top and bottom. And the function is going to be a function of the variables. And the variables are going to be laid out in any way that we choose to get the desired function. But within each meta switch, there's going to be many, many copies of the micro switches that will all go on or all go off if we set the variable to 1 or 0. Is this clear? I don't want this slide to confuse anybody. OK, so before I begin talking about what this buys us, any thoughts? So here, what does this redundancy, because we're paying a huge price here, the total size of the circuit, if we have, in this case, I've shown 16 micro switches for each meta switch. Here, I've increased the size of the circuit by a factor of 16. It's 16 times bigger than it would have been otherwise. What does it buy us in terms of the probability that it computes correctly? So, Jack, what are your thoughts?
I think not a whole lot. I think it would make more sense if they were like wider and shorter. So it matters if it connects top to
Yeah, that's interesting. Wider versus shorter. Very interesting. Yeah, that might be true. So laying it out in a square might not be a good idea. But so a big assumption here is going to be that all 16 of these little guys are independent, meaning they don't, if one of them fails, it doesn't greatly increase the probability that all of its neighbors fail too. And that could be an issue. Maybe that's not realistic. But assuming that's true, does it bias anything?
I don't think so.
Well, yeah, but that's what I'll show on the next slide. We need, in general, a lot more than one micro switch to fail. Because look at the cases here. The top, we had 3 switches that failed. And we're only looking at the on case. But in the on case, we still have a nice connection from top to bottom. So 3 switches have failed, and we have a nice connection from top to bottom. Here in the bottom, or in the lower part, we have 2 switches that failed, but we still have no connection between top to bottom. So it's supposed to be off, and it's actually off. So here, switches have failed, and yet we still have correct behavior. So it seems to bias quite a bit. But what are your thoughts? So obviously, I think I'm going to say something interesting about how we should lay out not so much the micro switches, but how we should lay out the macro switches, because there can be a concern here. So what are your thoughts? So Jack, your intuition was good. Like, I mean, I'm not going to talk about whether it should be rectangle as opposed to being a square, but your intuition was that if we're interested in top to bottom, we're interested in ensuring that we always get a top to bottom connection through each cell if we're supposed to get one, and we don't if we're not. And so the width versus the height seems to matter. But any other thoughts on this?
There can be many more sneak paths.
Sneak paths. Yeah. So recall that last time we were playing the game of Nibbler, which was the snake going around. And the sneak path was the possibility that there would be some diagonal path that we wouldn't anticipate. So why would there be many more sneak paths here?
Because you're multiplying 1 with 16, and there will be shorter sneak paths.
Yeah. So the interesting little twist is very related to that. Your intuition is good. But in the ideal case, when all the switches are on versus off, then it just behaves like a larger block. So if we've designed the meta circuit correctly, we shouldn't get any sneak paths just because we have larger blocks, right? Agreed?
Yeah, but depending on which switches fail.
Which switches fail? Yeah. But to play devil's advocate here, the whole point of the redundancy is so that if some of them fail, we should still be able to block top to bottom. So why would we get more sneak paths unless enough of them fail so that it's on when it's supposed to be off? Any ideas? I don't know if I'm setting this up to be an interesting problem, but there is one. Yeah. Right?
It would be the sideways. So say you
Yeah,
have
very good.
two that are on here and an off here.
Yep.
You just have this upper corner
Yep.
on the one that's supposed
Yeah.
to be off, then you can connect the.
Very, very good. I think that's where you were going with the additional sneak. That's exactly what you were saying. Good. Okay, let me try to explain that. Okay, so I just showed this. Okay, so here's just an example. Perhaps I should have started with this instead of the messy slide. But what I'm talking about, at the larger level, you've got ones and zeros that you program in terms of the variables. And at the lower level, the micro level, you have switches that are on and off. In ideal case, I'm switching between 9 and 16 for my blocks. But here, I have 9 that are off versus 9 that are on versus 9 versus off. But the overall path should remain the same, or the overall presence or absence. Okay, so now keep in mind what I was saying, and I'm going to make a digression into what I think is an interesting topic. It's going to be the topic of percolation. Yes? What's your name? Pardon, with a V?
Yeah, with a V. You can just call me V.
Just V? If you don't mind? That might be just V. Okay.
My question is, like you said, that all the micro switches have equal probability
Yeah.
of failure. Would it be of any advantage if we change the probability of some of the micro switches, like of failure, like make it lesser than the other micro switches, like so that it always finds a zigzag path from top to bottom? Would that ensure?
It's interesting, but I'm not sure I quite understand. So you're suggesting that we can control the probability, or?
I'm saying like the objective is to get the transmission from top to bottom. So it could be any path, like zigzag.
Yeah.
So, and it depends on the arrangement of the switches. So what I'm saying is, if the design, it's a square right now, maybe if we use a rectangle or triangle, maybe the diagonal switches have lesser probability of failure.
Sure.
And maybe that would be advantageous that at the end it has a higher probability of not failing as a whole.
I like the idea a lot of triangles or rectangles. I've never thought about that, but
like not keeping all the switches, micro switches having the same probability.
I see.
That's what I'm saying.
Yeah. I like the suggestion, but I guess the premise here is that the probability of failure of a switch. So the probability of a failure is something that is not under the control of me, of the logic designer. It's the people who build the technology who are striving to ensure a low probability of failure. And they're not really succeeding. They're building technology that has very high. But I don't think that's something that, in general, we can directly turn with a screw. We can't say, okay, well, maybe we could by using the sorts of tricks that people use here, saying, okay, well, this block is super important, so we'll make these much larger so that they have a lower probability of failure, something like that. But the ideas of different topologies are interesting here, as opposed to just using a square, because the topology is going to be key. Okay. So this is a bit of a vapid slide. But the nonlinearity is going to be the key here, in a sense. So what do I mean by nonlinearity? We saw an example of computing with probabilities a few lectures back where we were talking about setting up a nonlinear response, a thresholding response. In some sense, achieving a nonlinearity is the holy grail of circuit design at the level of devices. Linear systems are boring. If you just have resistors or capacitors, you don't have very much computing power. But when you introduce a nonlinearity, that's when, or a transistor, that's when you can build interesting functionality. And ever since, I guess, the 1930s and 1940s, when people were playing with and inventing transistors, this has been the objective of device technology, to get a good, and in essence, the sharper the nonlinearity, the better. So if response to the input, you can get a very hard thresholding on the output, then you've got a device that works well. And a very steep nonlinearity translates to rapid switching time. So you can go just a little bit and bang, suddenly the output changes from 0 to 1. So in other words, you can get zeros to ones that flip. So the nonlinearity is everything. So can anyone anticipate where I'm going with this? How is the nonlinearity going to come into play when we talk about sneak paths as they exist in the nanoscale technology? So Ryan, any ideas? How's the nonlinearity going to be interesting here? Ryan, right? Not Brian. Okay. So a little digression into percolation theory, which is a very interesting topic. Has anyone heard of percolation theory or taken courses on it? What about the chemical engineering folks? Because this is going to be much more a physical, a topic in physical chemistry than anything else. Here.
We do diffusion theory.
Okay. So how does percolation come into play there? And what is percolation?
I would assume you have some sort of point source that's radiating outwards.
Uh-huh.
And we modeled the progression of that over time, initial concentration.
Uh-huh.
Yeah, I don't really know what you're looking for.
Yeah, agreed. So percolation is, well, there are two aspects to it. I'm trying to formulate in my head a joke that has to do with a coffee machine, and I'm not succeeding. There's the topic that is very much a topic in physics, and advanced courses in physics will talk about percolation occurring at boundaries between materials. But then there's the mathematical topic, and the mathematical topic has a very interesting history. So first I'll have to set up what is percolation. But in a purely mathematical sense, with a very clean model of what's going underneath, you can very easily observe this phenomenon. You can just set up a simulation. And this will be one of the homework topics to do this. You can do it by hand, or you can do it with a simple for loop in a computer system to observe it. But the interesting part is that even though it's so easy to observe and the model is so simple, mathematicians really, really struggle to prove that percolation happens. And it seemed like an open problem and an insoluble problem. But then an old crank at Cornell solved it in the 80s, when nobody expected that he would. He solved one aspect of the problem. And so it has an interesting history. But what is percolation theory? Let me start by giving some examples. So here's the classic example, if you read about it. Maybe this isn't the initial example, but let's start with it because it's close to our model. Suppose you have a parking lot, asphalt, and you've got north end of the parking lot, south end of the parking lot. It starts to rain in the parking lot, so water's falling You guys know what rain is. Water's falling from the sky. And as the water's falling from the sky, it begins to form puddles in the parking lot. Initially, you just have very small puddles here and there. So this is my take on it. Since we want a north to south connectivity, imagine we've got a minnow, a fish. The fish can't walk on asphalt. The fish wants to swim across the parking lot. The question is, when can the fish swim across the parking lot from north to south? Initially, fish can't, because you just got little puddles forming here and there. But it continues to rain. As it continues to rain, the puddles get bigger. So now let's talk about the probability that the fish is able to swim across the parking lot as a function of time. What do you think that graph is going to look like? I guess it's no fun because I'm showing you on the screen. But as a function of time, the probability that the fish can swim is 0 at the outset, and pretty much exactly 0 for quite a while. And then suddenly, when it rains, we've got many puddles. The puddles are getting a little bit bigger on average. And then suddenly, bam, it just happens. That the probability that he can swim, it doesn't go up gradually. It's not like this. It goes up very steeply and very quickly. So you have a massive nonlinearity. And that's interesting. Why does that happen? So, and then you can come up, when you take a course on this, perhaps they'll start with many examples, but you could come up with thousands of examples from everyday life. Another example is if you have, this is the example that the original authors gave, if you have if you have a sponge, or is it a piece of hollow stone? So maybe if you have a piece of, what's the type of stone that has holes in it? Pardon me? Pumice, right, pumice, the very light stone. So if you have a piece of pumice and you start pouring water on the top, what is the probability that the water flows through the piece of pumice? Well, as a function of the size of the holes inside the pumice, it'll have exactly this property, that if you had a knob and you could turn the knob and increase the sizes of the holes through the piece of pumice, you'd have almost 0 probability that it goes through until you reached a critical size when all of a sudden, with probability nearly 1, it would go through. Okay, now so this is still very physical. We're talking about puddles of water, and we're talking about pieces of pumice. But what is a very clean mathematical abstraction of this? So Chopin, what's a clean mathematical abstraction of this? How about switches that are connected? Or how about, to make it even cleaner, I guess this is as clean as the switches, but imagine that you had, does everybody know what a graph is? Because I'll start talking about graphs, and people will assume that I mean, x versus y. But the mathematical definition of a graph is a collection of vertices and edges joining the vertices. How many of you guys have heard that? So a lot of you. It's surprising that this is an example of terminology that people will assume when they're talking and can massively confuse the audience. So if you're giving a talk to biologists and you say, and now we'll assume a graph model. And they'll say, okay, if this guy's talking about statistics, he's talking about plotting things in, what's the plotting tool for Microsoft? I guess Excel plots. And they won't understand that the guy's talking about a mathematical concept. But you've got vertices, and you've got edges connecting the vertices. And so now, as your random model, we have vertices. And now this is where the mathematics comes into play. Suppose that we have an infinite graph. So it goes these vertices, the plane goes off to infinity in all directions. Mathematicians often assume infinity. And assume that the placement of your vertices is random. Or you don't even have to assume that. Assume that it's a grid. I haven't drawn it as grid, but assume that you've got a grid that goes off in both directions. And so the placement of the vertices may be very regular on your grid. But suppose that the probability that a given switch is connected to its neighbor is just that, a probability. So it's a random connection. And so each vertex will be randomly connected to his neighbors with probability p. And probability 1 minus p, he's not connected to that particular neighbor. And then as a function of p, we plot the probability that you can reach any region of the grid from any other region. Or if you're the minnow swimming across the parking lot, you can swim all the way across it. So here, if it goes off to infinity in both directions, what's interesting from a mathematical standpoint is that, and this almost defies intuition here, this nonlinearity is a perfect step function. So the probability that you can go from infinity to infinity is 0 until you hit the percolation value, and then it goes to 1 in a single step, in a single minuscule increment of the probability. So once you start talking about infinity, strange things like that happen. But what's more interesting is you guys can see something on the graph here. Well, if you guys have been staring at it, so Jack, what's interesting about this graph? The probability isn't 0.5. You just expect that it was 0.5. It's not. It's, in the case of the switching model that I'm describing, it's, I don't know, I can't remember what it is, something like 0.67. So the actual value at which it occurs, at which percolation occurs, for some models is 0.5. Those are the boring models. But for other models, it's not 0.5. It's above. So there's this asymmetry. That makes it interesting. And the open result, so proving that percolation occurred at this specific value, you can easily establish by simulation. You can just, in a half hour, write a piece of code that simulates this with randomness, and you can very accurately compute it. But proving it proved to be very difficult. Okay. Just one anecdote about an interesting application of percolation theory, and then I'll return to the switches. But the interesting anecdote is this. So this is how I came to be introduced to this topic. When I was in grad school, I had a good friend who was doing research on ad hoc networks with cell phones. And he was funded to do this by some of the telecom companies. So the idea is that the companies that build cell phones, this has been a very successful technology, but if you've ever been to a sporting event, like if you've ever been to a Gophers game, you've probably noticed something. Your cell phone doesn't work. You just can't get a signal. The reason for this is simply that you have a huge concentration of people. You might have 30,000 people who all are trying to text from their phone. So they all want a connection. But the cell towers are arranged geographically, and a cell tower can only handle so many connections at a time. So this was a problem. So they came up with the brilliant idea of the so-called ad hoc networks. The ad hoc networks is, instead of having each phone communicate directly with the cell tower, let's set it up so that phones try to communicate with each other first. And so each phone tries to communicate with other phones. And this way you can route data or you can route voice, not by having the cell tower talk to each individual cell phone, but have it just route it, basically form an internet of phones as your mini internet in place. So, and this is an idea, and I know that Motorola used to have this functionality, and I think one of the phone companies, Sprint, for a while had this feature where you could have free minutes if you were using, they sometimes called it walkie-talkie mode. Does anybody remember this? Does it still exist? Does it still exist for Sprint, this walkie-talkie mode? I don't know why it wasn't more exploited. But anyways, here was the research problem that they posed and that my friend Massimo solved. The problem was, suppose that in the extreme of this model, you want to even do away with the grid of cell phone towers that exists and go for much more sparsely located cell towers and try to see if you could simply use this functionality to have very reliable cell phone service. But the model then is, for each cell phone, it has a limited amount of power. So it can broadcast over a certain radius. So imagine that each cell phone is, I think I've got, let me show you the pictures. Okay, so here's a picture of this. Each cell phone is a point that has a certain radius around it. And for this to be a commercially viable product, you want people to almost always have cell phone connectivity, at least in urban areas. So here's the question. As a function of the power of each cell phone, so as a function of the radius of power that they have, what is the probability that every person is always connected to some other person who's connected to some other person who's eventually connected to a cell phone tower. So in other words, if you assume that Minneapolis is a parking lot and the minnow is a signal that can swim across the parking lot, what is that probability? And the people from the cell phone companies, they were really struggling with this, meaning they were trying to calculate it. And they were saying, wow, this is a very difficult calculation. And Massimo, my friend, he made the connection. He figured out that there's an entire theory of mathematics, well-grounded in physics, that deals with percolation theory that solves it. So it was a very nice application of mathematics. And he was basically able to say, look, here's the percolation threshold, where beyond, so here this is, this model applies both in terms of probability, or it applies in terms of the radius. So here, for a radius of a certain size, with probability nearly 1, everybody's always connected to everybody. With a radius slightly smaller than that, nobody's connected to the tower with high probability. And you just have to figure out exactly what that is. So anyway, it's a nice application of it. All right. Yes, please.
So this actually depends on the power of the cell phone itself, not so much on the power of the tower. So that's not something the mobile companies.
Well, I guess it depends on the power of the tower, in the sense that the tower, if it has a lot of power, can connect with a lot of people, at the boundary.
Is it like you're using like a cell phone as a mini tower?
Yes. Well, here the idea is that you're using the cell phone as a mini tower to talk to your neighbor, and then your neighbor is using his as a mini tower to talk to some neighbor. And you're using a protocol that tries to find a path automatically through the area that's connected. There's an app that came out that I actually bought. It's called Tiles. Was a Kickstarter project. I have one, where it's attempting to do the same thing with Bluetooth. So I have one of these. And I actually bought 4 of them. This thing has a battery life, they claim, of 2 years. You stick it anywhere, and you should be able to track your objects. How's it working? Well, it has Bluetooth that's running, and any cell phone that has Bluetooth running the app, will try to talk to it and find its location. And then it routes the location of all the tiles in the world through this swarm of connectivity. And it's an app that could take off, because imagine you could embed one of these anywhere. They're very cheap. They're like $5 each, and be able to track everything. But it depends upon every tile that you have being within range of a Bluetooth device that's running the app often. This isn't different, because here, locating it, you're happy if you can locate it once every half hour if you've lost it. But it depends upon this particular product really taking off, which it doesn't seem like it is. Yeah, John.
I have a question about this scenario.
Yeah.
It seems to me that this relies on the fact that the tower could handle like that amount of data per time, have a large enough bandwidth, and handle the number of people. It's the connections that's the limiting factor.
But it's actually the opposite. So for the tower, handling the stream of data, once it's in its computer systems, is not a problem. And from the tower, it's got a big fiber optic link running through the ground. So getting the data, so the problem is establishing the individual connections. And the problem is actually radio bandwidth. If you look at like the technologies like CDMA, where you've only got and part of the problem is that the emergency services in the US, so fire and police and forest rangers and the military, they get something like 95% of the bandwidth. And all the commercial traffic is limited to 5% of the traffic. And okay, I am all for emergency services, but this is a bit drastic. The companies are really squeezing everything in the can out of 5, and if they would just increase it to 6 or 7, we would have much better cell phone connectivity. But anyways, so that wasn't your question, John.
I guess I didn't phrase it well enough.
Yeah.
Are we assuming that like a cell phone can handle all of this data from all the others?
That's a good question. That's a good question. Yeah, that's a very good question. But if you think of the model, if it's dense enough, a given cell phone doesn't have to handle the traffic from all of them. It's an entirely different topic, and one that I'm interested in, which is load balancing of traffic across a network, which means that this guy doesn't have to take all the traffic. The traffic can flow like a continuous plane through a lot of the phones. But yes, each individual phone will be handling other people's traffic. Yeah. Okay. But let me turn the discussion to switches and why this particular topic was of interest for the nanoscale switches. So here's just some pretty artwork that Massimo did for the percolation threshold, and he had nice animation going where there would be the colors and the probability of connectivity. You would see, if you'd play the video, it would go from here, each color is a disconnected island or a puddle. And as you'd increase the probability of connection, it would just go from many, many islands to one island, and just like that, bam. Okay, but enough on general percolation theory. So in terms of the switches, I'm asserting this without proof, and I, in fact, don't know how to prove it. This is a problem with a lot of percolation theory. But I would just argue that the model that we have for redundancy of switches in the micro level, at the micro level, is exactly the model of percolation, in the sense that if we look at the probability of a given switch failing or not failing, that's the probability of a vertex being connected to its neighbors. And so as a function of, so here on the x-axis, what I'm plotting is the probability of local connectivity. So the probability that each microswitch is connected to its neighbor. And on the y-axis, I'm plotting the probability of global connectivity, so the probability of a top-to-bottom connection. And you can see here, this is a poorly drawn graph, but I've got different curves that correspond to the number of micro-level switches. So if we have just one micro-level switch, which means the micro-level switch is a macro-level switch, what we have is just a straight line. So why? It was Jacob, right? So why a straight line?
Because the global connection is the same.
Exactly. So here, P1 is P2, so it's just a straight line. But as we go to, I don't know, I can't remember what these are. This was maybe 4, 8, 16, 32, and this is infinity. You can see that it doesn't take many switches before you start to get a nice nonlinearity. So great. Problem solved, right? This shows what I was arguing before, that redundancy actually buys us a lot. It buys us a lot in the sense that we get reliability in terms of the top-to-bottom connection at the cost of extra switches. But the nonlinearity actually means that we're getting a lot of bang for our buck. So if we double the number of micro-level switches, we're getting almost perfect behavior with very high probability in terms of top to bottom, but not quite. So Ryan and what's your name? Vibath. I haven't answered your emails, right? Yeah, sorry about that. We're getting perfect behavior, but as students anticipated, there's a catch. And the catch is the sneak paths. So here, so it was 1, 2, 6, 24, and 120. And then infinity for the lattice sizes and lowercase probability. So to make the discussion concrete, let me just introduce some terminology which we'll call the 0 margin and the 1 margin. So the 0 margin is going to be, and this is just a purely subjective measure, but the 0 margin will define to be the region along the x-axis for which we reliably get a 0, so no connection, as a function of the probability of getting a 0 to 1 defect. So here, the x-axis is the probability the switch misbehaves, but it misbehaves in both directions. So here we're supposed to get a 0, so we're supposed to have all white, and we start to get some blacks. So how far along the x-axis can we go while we still have a definite 0? And off on the other side, we have the 1 margin. The 1 margin is the area where we're supposed to have all black, but we start to have some white squares. And as a result of having some white squares, we increase the probability. We don't have a connection, but for what region can we still call it reliable? And the 1 versus the 0 might be defined as a probability of less than 0.01 of not getting what we expect here. Okay, am I losing people here, or people are following? Okay, so here is going to be, let me skip over this and come back to it. So here is the intuition. And this intuition nicely illustrates why we have this asymmetry. So again, Ryan, why the asymmetry in the 1 margin versus the 0 margin? You notice the graph wasn't a perfect S shape. It was so why? You had it before. It has to do with the sneak paths.
Right. So when you have 2 diagonal, it only takes 1 in a corner.
Very good.
To create a sneak path.
Perfect. So that's what we'll show. But why can you never get that in terms of the 1 margins? Why will that only be a problem in terms of the 0 margins?
Because there's 0 margins not going to create a sneak path.
Yeah. Okay, perfect.
Yeah.
I think you've got it all arranged up in your head. To me, this is not at all obvious until we started working it out. Okay, so just to illustrate. So the claim is the 1 margins are always good. So we never have to consider the problem of the diagonal sneak paths in terms of the computation where it's supposed to be connected and we want it to be connected. Why? Well, here's an example. We have 0, 0, and 1, 1 at the macro level. So that means that we want the function to evaluate to 1. And now what we're going to do is we're going to start introducing defects. When we start introducing defects, that means the probability of the micro level switches being correct goes from 1 and it drops. So the illustration there, I'll repeat it because I was babbling, is initially probability of micro level switching working is 1. Or the defect happening is 0. So we're all the way here. All the squares are black because they're always black when they're supposed to be black. As we start stepping down the x-axis, now the probability that a black square is black is not 1. It's going to be a little bit less than 1. And so that means that we do start to have some probability of defects. The probabilities of defects means we start having some white squares popping up. So white squares popping up means that we could get a connection. We could get no connection from top to bottom. But the likelihood of that happening is just the percolation likelihood. It means that we actually have to have a lot of white squares pop up before this happens. So now it finally happened. We finally blocked the connection. But if we look at the graph, then the graph will look like this. So for the 1 margin, it'll be nice and solid. Okay. For the 0 margins, in some cases, the 0 margins will be good. The 0 margin will be good. So in this case, if we have 0, 0, and 1, 1, everything will be good for the same reason that here we're supposed to have no connection. So we're supposed to have no connection between top and bottom. And so here, what we're going to do is, again, start introducing defects. And those defects will be white squares turning black up there. And it takes a lot of them before we get a connection when we're not supposed to have a connection. So then, bam, we get a connection. So here, we've got percolation. We've got the effect that we want. We have a good amount of error tolerance as a function of the probability of these small switches happening. But the pathological case, or the case where things go bad, is in the case of the possibility of sneak paths. And the asymmetry here, perhaps it's not so interesting once it's phrased this way, but the asymmetry has to do with the fact that by virtue of the fact that we have 4 connected switches, so we have switches that have 4 connections, we will not get top-to-bottom connectivity across a diagonal. So if we were to lay out our function like this at the macro level, the function should evaluate to 0. Does everybody see that? Because the macro level switch, remember, it's a 4-connected switch. So the 4-connected switch is only connected to its east, north, south, and west neighbor. So there's no connectivity across the diagonal. But blocking a path, you can block a path in the other direction with diagonals, in a sense. Does that make sense? So anyways, here for the poor 0 margins, what can happen if we go to the black and white type of representation is here we can have no connection. So we're not supposed to have a connection between top to bottom. But suppose that some of the black squares start to turn, or some of the white squares start to turn black. Well, bang, very quickly we can get a connection. because it just takes a few right around the diagonal, maybe just one around the diagonal, and we get that connection. So in this case, what does the graph look like? Well, crappy. That's not a very good nonlinearity. Does it make sense? Okay, so this gives rise, and all of this was to set up, because in the end, the kind of research that I do always has this flavor. You consider some interesting setup, but the research gets interesting when there's a puzzle to solve. And all of this was a setup for the following particular puzzle. Return to the topic of how do we assign variables to points in the switching lattice to obtain a function. That was the motivation. And now we have an additional constraint. We want to assign variables to points in the lattice to compute a particular function. But we want to avoid the poor margin cases, and that can be stated very simply. We want to avoid cases where we have diagonal connections in the case of the function evaluating to 0. So how can we do that, Ryan? That's a bit of a leap here, but I'm pressing you because then hopefully it keeps your mind going throughout the lecture. Anyone else? It's going to be similar to the concept that we had before. We're just going to make use of duality, and we're going to make use of the f function, which is the top to bottom, and the g function, which is left to right. Yeah, Jordan.
Are we pretty much just applying dual to the micro switches?
It's a good suggestion, but the dual, in fact, we're just going to apply it at the macro level. And the duality at the macro level is going to be sufficient in terms of how we lay it out. Meaning, the layout that we're going to choose, which is we have the function that's the top to bottom, and if we have its dual, that's the left to right, then for free, we get this property that we never have the diagonal paths, hence we have good error tolerance. So let's remind ourselves what we meant by that. So first, this was implicit, I suppose, in what we were discussing last time, or at least perhaps I should have explained it better. But we have an expression, a 0-1 function or a Boolean function, and it's going to be set up as the OR of AND terms. That's the form we're going to use. And that form, in a sense, directly corresponds, or doesn't directly correspond, but in a sense corresponds to the lattice layout, meaning that a path from top to bottom is going to be the AND of the individual variables we choose. So we get a path from top to bottom following this particular path. If this variable is 1, this variable is 1, and this variable is 1, and. So the AND of the variables in a path from top to bottom is one path. And then the overall function that we get is going to be the OR of all the paths that we can get. So that's just a simple sum of products representation, where sum is OR and product is AND. Okay. So here is far more text. My advisor, he gave me lots of good advice on giving a good talk. His advice was always very simple. 1, never show anything on a slide that you don't explain. And 2, basically never have a full sentence or more than a full sentence on your text. Never show a paragraph on a slide. And different fields have different cultural expectation when it comes to talks. So in chemical engineering, people give very different talks, don't they? Sort of. Yeah. My sister's a biologist, and the rule of thumb is, if your talk is 20 minutes, you should have 5 slides. And each slide is going to pack a tremendous amount of information. So you're going to spend 5 minutes on each slide. And in some fields, in the fields that are closer to the device or the material level in electrical engineering, people have more or less the same tradition. But as you can see, my style in general is, and so like I have a colleague, Chris Kim, and when he sees the raw PowerPoint slides for my presentation, he says, okay, so your first slide, you've got a green box. And then on the next slide, you've got some arrows coming out of the green box. And then you've got another green box inside the green box. And that's it. That's going to be your talk. And, his slide always contains device measurements and graphs and stuff. Anyways, but no paragraphs here. But where I'm going with this is exactly what I just said, is that in order to have good margins, all we have to do is ensure that the top-to-bottom connectivity, that function, is the dual of the function that we get from left to right. In general, we don't get this for free. So if we just lay out a function from top to bottom, the function from left to right will not be its dual. So we have to do some work. The work we have to do is what I described last time, is you first compute the dual, and then the choice of where you assign the variables will be you take the terms laid out on the column headings, the terms laid out on the row headings, you pick the intersection variable. But that's all you have to do. When you do that, you get the function from top to bottom, and you get the function from left to right that's its dual, and you get this property of error tolerance here. So why? Well, okay, this is just a computation of the dual, but here's the illustration of it. So if we have the function that's from top to bottom, recall the definition of duality. The definition of duality is you get the dual of a function by complementing all the variables and complementing the function. So complementing all the variables means whenever the variable is 1, in the new expression, you set it to 0. And complementing the function means that if the function evaluates to 1, instead, the function should evaluate to 0 and vice versa. So consider the function here on the left-hand side. This is the function, that an example of the function that evaluates to 1, because there is a path from top to bottom. So now this is where you have to do a little bit of imagination in your head. In terms of the dual function, imagine that I flipped all the 1s to 0s, because that's what I do in the computation of the dual function. That means that this would be a different case. This is a different input case. But in a different input case, I would now have all the 1s flipped to 0s and all the 0s flipped to 1. But the point of the argument is that if I would have a connectivity from top to bottom for the function, so that function would evaluate to 1, then the dual function, which is the function from left to right, would be the function where, in evaluating the dual function, I would flip all the variables, so I would have all the 0s. And now that function from left to right would have to be 0. So why would it have to be 0? I keep forgetting your name. Chris? Alex. There's another Alex. Alex. So why? Why is the left to right function here 0? Oh, just like even in this example, what's on the slides here. Here on the right-hand side, why is there no connection between left to right?
Because we knew that there was, by swapping them, we created a path.
We've created a path. So if there is a path from top to bottom in terms of 1s, then if we flip the 1s to 0s, that path now will block left to right. There's no way to get from left to right if we have to go across, imagine this is a path. I don't know what this is. Is this an electric fence or something? There's no way to get across the electric fence if the electric fence runs from top to bottom. There's no way to get across it from left to right. So just by the definition of duality being a function that we obtain by flipping all the variables and flipping the function, that means that here, whenever the function f, which is top to bottom, evaluates to 1, it means the function g, which we obtained by flipping all the variables and complementing the value of the function from left to right, will evaluate to 0. And that's going to be enough to ensure that we never get the diagonal sneak paths. Does that make sense? So I don't know how much of this makes sense, but perhaps you can digest it. It was intentional here that I'm not going into any of the details of what we do to the Boolean functions, how we prove this, any of the logic design part, because it's not the emphasis. But I think the percolation argument is interesting. The randomness argument is interesting. And here, the duality property is interesting for the functions. OK, so once again, I've taken more time than I should have. But next class will actually begin in chemical kinetics. But in the minute that we have remaining, any questions on this? You guys will get the first homework finally tonight, now that we're done with this particular module. And you'll have, I guess, 2 weeks to do the homework. So you'll have questions then. John, any questions? You look. OK.
I might go neighbor, might just go straight home. Okay, if not, I'm tired to say. I'm tired.
Take it anyway.
Analog IC design. I don't know, I just emailed the professor and said, this is the first I've heard about it, so. Sounds like it should be.